f on the interval 0, 1, and what this says is that there must exist a c on the interval 0, 20. There exists a c on the interval 0, 20 such that f of c equals 0. I'm waiting for the oh. Do you get it now?
I don't. So is the problem before that you can't prove that they cross?
Yeah.
But if one is smaller than the other and then it becomes bigger than the other, then obviously they cross.
Yeah, that's what we just proved.
Right, but.
Yeah, but you're just saying obviously they cross. And you're saying just because they're continuous, they just must cross, right?
Well, if
I basically agree with you. But here, I mean, the reason is the intermediate value theorem. Like I mean, unless you want to do some kind of epsilon delta proof or something, right? But I mean, I basically agree with you. Yes, if you have two continuous functions and one starts high and ends low, and the other one starts low and ends high, they must cross. And the reason is, or the way you prove that very, very common sense fact. I mean, that's about as common sense as the intermediate value theorem itself is, right? Right. So the way you can prove that fact is using the intermediate value theorem by turning them into a single function. That's essentially what we've done here, right? The mountain is just to get you thinking about the story. What we've really shown is that if you give me two functions that are like one higher and one lower, and then they swap, then they must cross somewhere. That's basically what we've done. Yeah. So there must exist a point such that f of c is 0, and just to finish it off, since f of c is s of c minus r of c, and that's 0, I have thus found a point C where S of C equals R of C. And the general technique is, if you want to show that two functions are equal somewhere, instead construct a single function, which is the difference of those two, and show that it's somewhere 0. Who is with me? Everybody. Good. Mountain problem. All right, more. There were a couple other interesting problems. Were there even?
Yeah.
I feel like there were. Oh, from the next section, from 2.5, should we go over a couple? Alice, give some suggestions. Or we could definitely do 18.
Wait, what is that from that section?
I think 18 was on the next page, right? This book split up infinity into its own section, which I thought was not that. 53. We can do that. Let's do 18. Let's do 53. Let's do I don't know. 37, 24. Sure. What did I just say? 37? No, 30. What was that one with all those E's? Was that 37? Yeah. 37, 77. Can we put these up real quick?
Yeah.
5 people. Raise your hand if you didn't put a problem up at the beginning of class. Should be exactly 5 people. Can you do one of these now? Go. Let's just take a minute. Then we are. We'll talk about a couple of things. Oh, I remember the other cool problem. Was there some problem like 121? Yeah, but the same night, right? Just different previous section?
49. I was on the mountain section.
Yeah, that's right.
121. That was. Wait.
And I don't even know but I kind of.
We also lose that. No, that's 85. It's only like 100 people.
121 was this function that was like, see this problem? That was kind of interesting. The function was 4 over 1 plus 2 to the 4 over x. And they asked you for the limit as x approaches 0 and the limit as x approaches 4, is that right? No, the limit as x approaches 0 from left and right.
Oh, and it's 4 in there are the answers.
Yeah. Okay, oops. So I want this asked for the limit as x approaches 0 from the, what did I ask for first, right or left? Right? Oh, okay. I don't know. One of you, doesn't matter. And I know it didn't ask us to do this, but let's just do it anyway. Let's also take the limit as x goes to infinity and x goes to negative infinity. This is kind of like a cool function. It's too cool for pre-calc.
Wait, what are you?
I'm doing 121. I forgot there was one more cool problem I wanted to talk about. 121.
Wait, for what?
I'm doing some stuff. I extended the problem slightly.
Yeah, I was like, what?
Yeah, they only asked for 2. So this problem, while they're finishing up on the front board, there was this problem 121 that I think came just after the mountain problem. It said, yo, there's this function 4 over 1 plus 2 to the 4 over x. Let's talk about this function. What is its domain?
Real numbers without zeros.
Yeah, I think it's everything. I think it's everything except 0. I certainly can't plug in 0. 2 to the anything is going to be positive, so that can never be -1. So I don't have to worry about the denominator being 0. So I feel like I'm good. All right, let's go through these one at a time. I mean, you did the first 2 for homework. So all together now, if I'm taking the limit as x approaches 0 minus, so now that's that x down there is a tiny, tiny negative number. Gerhard, you got this? All right. Gerhard, what's 4 over a tiny negative?
It's just basically like negative.
It's pretty much negative infinity. It's a huge negative, I agree. What's 2 to a huge negative?
Really small.
2 to a huge negative is really small. Can you be more specific?
Like 0 minus 0 plus.
0 plus? Yeah, that's relevant, right? Is everyone following this? We gotta like stay together like in rhythm, right? So if x is a tiny negative, 4 over a tiny negative is a huge negative. 2 to a huge negative is tiny positive. What's 1 plus a tiny positive? 1, but let's also care about whether it's more than 1 or less than 1. It's going to be a tiny bit more than 1. So if this denominator is a tiny bit more than 1, what's 4 divided by a tiny bit more than 1? Basically, the answer to the limit is 4, because the limit's a number, but I'm going to write 4 minus as a kind of footnote. Not only is the answer 4, but in fact, by our analysis, it's always going to be a little bit less than 4. Cool? Okay, let's do the next one. Limit as x approaches 0 plus. Now I do have 4 over a tiny positive. 4 over a tiny positive is a huge positive. 2 to a huge positive. Huge plus 1. Still huge. 4 divided by huge positive. 0, and in fact it's going to be 0 plus, right? Okay, now, what's up?
Couldn't you also turn this into like a logistic function?
Yeah, it kind of is a logistic function almost. We're going to find out in a minute. So now these are the 2 that weren't on the homework assignment. I'm giving them to you now. So let's do them all together. Ready? What happens if I plug in infinity? What happens if I let x go to infinity? So now 4 over huge positive. Tiny positive, that's 0 plus. What's 2 to the 0 plus? Yeah. If I plug in a number a tiny bit more than 0 into the 2 to the x function, it's going to give me a number which is a tiny bit more than 1. Good so far? So 1 plus a tiny bit more than 1, tiny bit more than 2, and 4 divided by a tiny bit more than 2?
2 minus.
A tiny bit less than 2. Cool? Okay, last one. Now if I plug in negative infinity for x, it's 4 over huge negative is going to be tiny negative. What's 2 to the 0 minus? 1 minus. Tiny bit less than 1 plus 1. A little bit less than 2. 4 divided by a little bit less than 2. A little bit more than 2. Okay, good. That's some calculus happened right there. So now I guess we can try to graph this function, right? What the hell does this function look like? Well, Oh yeah, that's lame. No, whenever it says use your calculator, that override those directions with don't use your calculator. Okay, if I plug in a number which is a tiny bit less than 0, it's going to be more or less 4. When I plug in a number which is a tiny bit more than 0, it's going to be more or less 0. There appears to be an asymptote of y equals 2. And as x goes to infinity, I'm going to be getting closer and closer to the line y equals 2. Do I ever cross this asymptote? You guys just like guessing?
No.
No.
Yeah, prove it to me.
Because
I think we could just do some math real quick, right?
Yeah.
Is it y equal to 2?
I don't know. Yeah.
As it approaches
I guess I could just like set it equal to. Is this even worth doing? Whenever I asked that question, I knew you guys would say no. It was a test. If I multiply, so then this becomes 2 plus 2 times 2 to the 4 over x. Can I do something here? Yeah, subtract 2, so that's 2 equals 2 times 2 to the 4 over x. And then like what? Divide by 2? Yeah, divide by 2. So I get 1 equals 2 to the 4 over x. But the only time 2 to the something is ever 1 is when the something is 0. And 4 over x can't be 0, so we're good, right? Okay, cool. So no solution, so it never crosses. I think I pretty much know what this looks like, right? It's just going to go, it's going to start here, and it's going to go, and
Are those open circles?
those are open circles. Yep, because it's not defined at 0. And in fact, yeah, this is like a, do you guys remember logistic curves from pre-calc B for like 5 seconds? This is kind of a logistic curve which got like cut and like pasted above or something. I don't know. All right, awesome function. And actually is a nice transition into a topic which you did homework on, but which we did not actually ever talk about in class. So let's do this really quick. And that is asymptotes. Although these have been around forever. I mean, you've been talking about this since pre-calc A. And I think you even got this. You even got this def. What's up? I want this in a minute. Yeah, we're going to go over the board. Let's talk about asymptotes for a moment. So I don't know which one you want to do first. Let's do horizontal asymptotes. So what is the official formal definition of a horizontal asymptote? Okay, let's do it. So f has a horizontal asymptote at y equals k if and only if. Can I get a formal definition, Magna? Not quite that it never reaches k.
Or it has a limit at k.
Yeah, specifically what kind of limit?
As x goes into infinity or negative infinity.
Yeah, exactly. That's it, right? We have a horizontal asymptote at y equals k if and only if, well, if the function gets closer and closer to k as x goes to infinity. So Magnus says this is going to be true if either the limit as x goes to infinity of my function is k, or she says we also call it a horizontal asymptote if instead the limit as x goes to negative infinity of the function is k. Follow? Yeah. And that's why we said that this has a horizontal asymptote. Okay, so this is just all the same stuff we did in pre-calc C when we talked about asymptotes, but now I'm giving you a formal definition in terms of calculus concepts. All right, let's do the other one. F has a vertical asymptote at x equals k if and only if what? Sandeep.
As f or as x goes to k, as x goes to k, f x goes to infinity or negative infinity.
Pretty much, right? Yeah. If the limit, you didn't use the word limit, but if the limit as x approaches k of the function is infinity. I have a kind of slight objection to this. What's the issue? Yeah, Mateo.
Different ways
Yeah, maybe like different ways, right? And there's really actually like there's actually a whole bunch of different cases here, right? Let's do them one at a time. So maybe it's true that only the limit from the right of the function is infinity. So perhaps the function, I'll make a tiny picture over here, right? Perhaps it's true that as x approaches k from the right, the function goes up to infinity, but maybe on the left it just does some kind of like, you know? Would I still call that a vertical asymptote?
No.
Yeah, I would. Yeah, I would. I definitely would. So it was a joke. Or if the limit as x approaches k from the left of the function is infinity, then I would also call that an asymptote. So maybe on the left side it's going up to infinity, but on the right side it's just like 2. Right? Yeah.
I mean, also negative.
Or maybe it goes to negative infinity.
Wow.
Yeah, so maybe the limit is x. Did I just scare
Can I just
you?
say absolute value? Yeah. I mean, that's the
Good.
Let's go really loud.
Good. Yeah. Limit as x approaches k. Whoops. Limit as x approaches k. So basically, okay, I'm kind of writing it out in a really kind of annoying, wordy fashion. But essentially, if the limit from either the left or right is positive infinity or negative infinity, then that is our official definition of what it means for a function to have a vertical asymptote. So what's going on here? It's doing this, and here it's maybe just kind of like doing that, and here maybe what did I say? Maybe on the left side. And then, what's up?
Didn't they used to tell us that you weren't allowed to be defined a vertical asymptote?
Oh yeah, that's just false, right? Do you have any objection to me just like putting a dot here? Seems fine. Nope. Yeah. So all right, if I ask you in the future, and I will, for some particular function, justify why this function has a horizontal or vertical asymptote, where it does, then what you're supposed to do is cite the appropriate limit and just say that it has the asymptote that it has. Cool? Okay. All right, Calvin, there are a couple more cool homework problems, or slightly cool at least. Let's check them out. I'm so confident they're right, I'm not even going to approach the board. We're just going to discuss from afar. 18. What was the question? Wait.
It was. Wait, what was the
Find the
question?
vertical asymptote.
Find the vertical asymptotes of secant pi x. Oh yeah, so wait, is that true?
No.
I feel like
No.
it's wrong.
No, that's wrong.
Yep.
It's pi over 2.
Yep, whoever did 18, you're wrong. I think. Wait, hold on, let's go check. No, it's not pi over 2. It's this is just a pre-cal question.
No, that was
Secant pi x. So if it's secant pi x, then that means that the period of that function must be 2 pi over pi, so that must be 2. So the period is 2. Aren't the asymptotes going to be at like -1 and 1?
No, I mean like the graph is wrong.
Oh no. The graph. Wait. What the hell's going on? They should be at
1/2 and -1/2.
Yeah.
So 5 halves.
Oh, yeah, the graph usually.
Yeah, there should be asymptotes at like -1/2 and like 1/2 and stuff, right? Yeah, I agree. There'll be an asymptote at -1/2, and there'll be an asymptote at like 1/2, for example, and at 3 halves. Sorry, whoever did number 18, you messed up. I'll watch the video later and figure out who it was. So yeah, right. It would have to be those numbers which got plugged into this function to make secant be undefined. So it's going to look like this. And so the answer is, by the formal definition of vertical asymptote, which we have now, there are going to be there will be vertical asymptotes at x equals basically anything in the form 1/2 plus k, where k is an integer. Right? Because it'll be one at like 1/2, 3 halves, etc. I think that's the right answer now.
Yeah.
People backing me up? All right, Alice backs me up. Good. 53. What is the limit as x approaches 1/2 of x secant pi x? What's happening now?
You have to
I agree with this answer. I think I do at least. Plugging in a half, the x isn't really doing anything, but secant pi over 2, this is exactly what secant pi x looks like. So I agree. It's going to go from 1/2 from the left, it's going to go to infinity. 1/2 from the right, it's going to go to negative infinity. And the question said what? Oh, just find the limit. The answer is no limit. It doesn't exist for exactly that reason. 24, kind of like minimalist job up here on the board. The question was, what was the question? Find the vertical asymptotes, if any. And the answer is there are no vertical asymptotes because upon factoring the denominator by difference of factor by grouping, we find that this, though it initially appears that there might be a vertical asymptote at x equals 2, we know because we're kind of experts at graphing rational functions that that's not the case because the x minus 2 cancels out. We're just going to have a graph with a hole in it, right? So this graph is this initial function is really might as well be the function x plus 2 over x squared plus 1, and we know that this function does not have any vertical asymptotes because the denominator is never 0. So they'll just be, our actual original function will look like this with a hole at 2. Okay, 37 was just some more or less algebra. Again, ooh, I like this person made a picture and everything. Excellent. So there was some weird function, and the question was, does it have any vertical asymptotes, or does it just have a removable discontinuity? Upon factoring the top, then we get some cancellation, and we see that indeed at -1 there's a hole, not a vertical asymptote. Is everyone okay with this? I feel like if you're good at pre-calc, it's not that hard. 77 asked you to come up with an example of a function meeting a certain requirement. It said, find two functions such that they each go to infinity, but the difference of the function is not 0. Let's see, who did this one? Each time is you?
Yeah.
Ethan Chen says, yo, give me this function 1 over x squared. That's certainly going to infinity as x goes to 0. Give me this function 1 over x to the 4th. That's going to infinity as x goes to 0. But when I take the difference of these two, I get negative infinity. Yeah, perfect example. Laura, question?
For something like this, would you be allowed to use a limit as x goes to infinity? Or
That's okay with me.
Like the ones with the square root.
Yeah, x minus x squared is a perfect example, right? Or x squared minus x, or anything really. Okay, can I have this homework? Can we put the homework over here? You're pretty much done with it now. I want to talk about like one other thing.
That's fine.
Okay, we have this whole back and forth act going on where you pretend that you're not having fun, and you know it's like a comedy routine. You're like, Miss Rose, I'm so bored. Can we just do nothing and be lazy?
Ooh, that sounds like a good idea.
And then you pretend like it's a bad idea when really you want to do
And
it.
and then you know I'm also just never gonna say yes. So
Yeah, that's true.
yeah, so that's why it's an act. All right, good. There's about one more loose end I want to talk about, and that is this worksheet called limit of the product of two functions. Can you take that out? I'm interested in hearing some of your kind of like solutions. Oh, actually, before we go over this, sorry, I keep changing my mind. Before we go over this, there's another thing I want to show you, and that is this thing called CalcChat. Some of you may have discovered, just the crafty members amongst you may have already discovered. Can somebody pull down the thing and turn off, that's right, we're going multimedia. Turn off the light also. Is that on yet? Is it coming on? See the green dot?
Yes, it's coming on.
Okay, so our textbook which we purchased in about, I want to say maybe 2005 or so. I think you have to turn all the lights off, or at least it's better that way. This textbook we purchased in 2005 is a modern textbook in the sense that it comes not just with pages, but also with all kinds of extra like crap. There's probably some CD-ROMs that all the teachers lost a long time ago. You know, oh, you guys probably think it's funny just to even say CD-ROMs, right? Oh man. I had to explain to somebody yesterday what a dial tone was, or no, not dial tone. What's it called? A busy signal. Like, what's a busy signal? I was like, oh my god.
What's a busy signal?
All right, so when you call someone and they're on the phone.
It's when you call someone.
It's still a thing, but it's pretty rare. Almost no one has it. Anyway, the point is that this textbook has resources. So if you will go to, let's Arun, can you get this on screen? Or maybe it doesn't matter. If you go to www.calchat.com, you will see this page that comes up. Oh, by the way, this is what I'm about to show you. Well, okay, let's just get to it. We have defined our textbook. Our textbook is this one. Calculus has a very exciting name. It's called Calculus, as 70% of calculus textbooks are called. But this one is the 4th edition ETF, which stands for Early Transcendental Functions, which means that we talk about sine and cosine like at the beginning as opposed to at the end. And then when you see the correct cover, click on the book. All right. Now we are at our book, in which you will find our solutions to all odd-numbered problems for basically everything in the entire book. So for example, take the mountain problem. That was chapter 2, déjà vu. Go to chapter 2, we go to section, I want to say that was 4, pretty sure. And then we go down, 107, mountain problem, solution. And here is not only the original problem, but a complete solution of exactly like what to do. Whoa.
Yeah.
All right. This is potentially an excellent learning tool, and it's also potentially terrible.
Yeah, that's all I'm saying.
Your grade, so I talk about this about every other year. Sometimes I don't talk about it, but they find out about it anyway because it's mentioned in the book, like in the margins of it. It says, hey, check the count check for this and such stuff. So, if you abuse this, it will just be terrible for you, okay? And so, you guys seem like a relatively mature group, so I'm not really worried about this, but there are certain bums who, like Jordy, Jordy's the first name that comes to mind. I'm just saying. Lazy people who just like scribble their homework, like one on the bus or whatever. So, what?
Mateo made up the Jordy of the bum thing.
I don't know how you got it. I must have just like passed it to you.
I think you might have mentioned it before, yeah. It's exactly what he is. I love Jordy. He's a great guy. But he could be a better student. So the point is, please try to be disciplined about this when you are doing your homework. Try to do the problem all the way to the end. If you're successful, great. Check your answer in the back of the book. If you got the answer right, move on. If you got the answer wrong, go back, try the problem again. If you're really, really stuck, once in a while, you can log on to CalChat and they might help you, okay? Some of their answers are not necessarily the greatest things, but sometimes they are. Okay, so that is a resource. Another resource is Wolfram Alpha. This is a great website. I think I bet a bunch of you know about this already also. This will just more or less do math for you. So this is what you do if you have some like partial fractions problem and you don't want to do it, or you want to check and see if you did it right. You type it into Wolfram Alpha and it just does all things. So let's take that function that, what was it, 2 plus, I forgot already, no, 2 over 4 plus, no, what was it, 4 over? I already forgot. 4 over 2 plus 2 to the,
4 over x.
oh yeah, 2 to the
It's like 1.
4
It was
over
1 plus.
x.
It was 1 plus.
It was 1 plus?
Yes, it does.
Yeah.
Oh yeah, you're right.
So it's just
So, yesterday when I tried to do this, Wolfram Alpha was like down, but let's see what it does. So you type that in, maybe things happen. Slow internet. What?
a lot of times you run out of competition.
It appears to be not liking this
That's why
function.
you like use a proxy and stuff.
Great, that's what happened yesterday too. All right, wonderful dramatic moment that we just had there. Anyway, try to go to Wolfram Alpha every now and then if you want to graph a function. It'll graph it for you. It could be kind of fun.
You know about Tor, right?
I don't feel the
Should I just give it an easier function and see what happens? That's a good idea. All right, Wolfram Alpha, can you handle x squared?
Oh.
Looks like you can.
Hey.
Maybe.
Wasting my time.
We'll make this again. It's like the same people make mathematical, right?
Yeah.
Wait,
What do
I
they call it?
don't
What's that-
think giving
what's that
it
company?
an easier function will cure its certain problem.
It might though. You never know what's
All right. Good. So I don't know. So that's that. All right. Lights back on. Pull the thing back up. Limit of the product of two functions. Let's talk about it. We did most of them together, right? Where did we stop? Where did we stop?
Got this.
Whoa. Could you maybe like erase that board also, or somebody? Let's see what Mateo got. Mateo. So we did a bunch of these together, and then it starts getting complicated right around 0 times does not exist. What do you guys think about 0 times does not exist?
Depends. I think it depends.
I agree with you. Yeah, I think it depends too. Can I get some examples? Mateo did some examples. Oh, he even like did this and everything.
X sin X.
Good. Yeah, he said what we are investigating right now is what happens when you're taking the limit as x goes to a of one function f and you get 0, but the limit as x goes to a of some different function g does not exist. What then can I conclude about the limit as x goes to a of f of x, g of x? And what can I conclude? I think the answer is nothing, right? I think that I agree with Mateo. When this is 0 and this does not exist, I think that the answer is indeterminate. Can I get some examples from the audience? Yeah.
X sin X.
That's like 0.
X sine x as x going to what?
Goes to 0.
Going to 0. Okay, so yeah, if we take the limit as x goes to 0 of x sine x.
Wait, no.
Good afternoon, Blazers. May I have your attention for a few brief announcements? Today
No,
at
as you go to
3:15,
infinity of 1 over
there will
x
be
sin
a
X.
softball meeting for all students interested in trying out in room 119.
1
And
over
that's
x
room
sin X.
119
Oh, like
at
that.
Yeah, there
3:15
you go.
for softball.
Okay, so this is going to 0 and
Also
this
today, there
does
is
not
high
exist.
school
And yet, what's the answer?
intervention. You should have been going to class now. High school intervention began on Tuesday.
Class, what's the answer?
It is from 2:30 to 4 o'clock. If you are unsure of your room number, please report to the counseling office. Hello, sophomores. The
You all
Achieving
just- you all
Collegiate
just shut
Excellence
down.
and Success ACES program is now recruiting. Will you be the first
Wait, what?
Need help filling out scholarship applications? Need help filling out
Yeah, this is definitely 0, right? Yeah.
This
It's definitely 0. This is a number between -1 and 1, but this is getting bigger because this is 0. Okay, but giving me one example is not the hard part. The hard part is giving me another example. Yeah, give me another example.
174 from 2:30 to 4 o'clock. The deadline to apply is Friday, February 6th, that's tomorrow. Again, today you may receive help in filling out the applications from 2:30 to 4 in room 174. Also, juniors and seniors, if you are planning on driving this semester, you must turn in an application and receive a spring